Hello everyone. So today we're going to go over entropy changes in the surroundings. So we went over how to calculate the entropy changes in the system. Now we're going to do it for surroundings. And the entropy change of surrounding as a result of heat transfer from the system to the surrounding. So, or heat absorbed or released to the surrounding can be calculated by taking delta H system over T surrounding. So we're trying to figure out, as a result of what happens in the system, in the reaction, for example, how that affects the entropy of the surrounding. Because remember, we need to figure out what the entropy of the universe is, the change in entropy of the universe, to figure out whether a process is spontaneous or not. If the overall change in entropy of the universe as a result of our process is negative, then that process is not spontaneous because the chances of it happening is much, much less than it not happening. So it's not going to happen. On the other hand, if as a result of our process, the change in entropy of the universe is positive, we are increasing disorder, then the chances of that happening is much higher than it not happening. Therefore, it does take place. It is spontaneous. So to figure that out, we learned how to figure out delta S change in entropy of the system. Now we're going to learn how the entropy of the surrounding changes as a result of the things that happen in the system. So delta S surrounding is equal to minus delta H system over T surrounding. So the way we change or affect the entropy of the surroundings as a result of what happens in the system is by either transferring heat to the surrounding or absorbing heat from the surrounding. So if you transfer heat to the surrounding, then delta H system is negative. But if you transfer heat to the surrounding, things move faster, so you have higher possible energy states, therefore you have higher entropy. So then the delta S surrounding should be positive. That's why we put a negative here so that the sign works. So if the delta H system is negative, you're transferring heat to the surrounding, so then delta S surrounding comes out to be positive, because negative of negative will be positive. Now, why do we have to divide it by the temperature of the surrounding? Because if the surrounding is already very unorganized and we transfer heat into it, we are not going to make it that much more unorganized. So if the temperature of the surrounding is very high, then the heat that we transfer into it will not affect its entropy all that much. It's kind of similar to like if your room is really messy, you have pizza boxes all over the place, your clothing, your chemistry notes, everything is all over the place on the floor. If I come in with my hamburger and eat a burger and drop a ketchup on the floor, nobody's going to notice it. So the entropy doesn't increase that much because it's already very high. On the other hand, if you are very neat and everything is spotless in your room, the floor is shining spotless, I come in with my hamburger and eat and drop a piece of ketchup on the floor, you're going to notice it right away. The entropy increases a lot more because it's already organized. So if the temperature is very low and you transfer heat into the surrounding, the entropy of the surrounding is going to shoot up a lot more than if the temperature is very high. So that's why this is the way it is, that formula. So once we learn that, then we can calculate the change in entropy of the universe based on things that happen in the system, because it's much easier to keep track of things that happen in the system. So we know that delta S universe is equal to delta S system plus delta S surrounding. Again, we're trying to see whether as a result of our process delta S universe is positive or negative, and whether therefore the process is spontaneous or non-spontaneous. So if I substitute this in for delta S surrounding and then multiply everything by negative T, and then I can call this delta G a new function which we call Gibbs free energy. So delta G is equal to delta H minus T delta S, and these are both system, delta H and delta S. And now since we multiplied it by a negative, if delta G is a positive, then the process is non-spontaneous because delta S universe is going to be negative. If delta G is negative, then delta S universe is positive, so therefore the process is spontaneous. And if it's 0, then delta S universe is 0, so then you're at equilibrium. Now, why do we do it this way? Not to make life harder for you. Actually, life is easier if you do it this way. Why? Because delta G is a much more informative function than delta S universe. For example, if the delta G for a process is minus 100 kilojoules per mole, as a result of that reaction. And then that means that once 1 mole gets converted to products, not only that process is spontaneous because delta G is negative, you also can get 100, maximum 100 kilojoules of work out of it. Because spontaneous processes happen on their own, and as they do happen, you can also use that energy that will be released to put to work. And so if delta G for a process is negative 100 kilojoules, that means that that process is spontaneous. And as it happens on its own, you can get a maximum of 100 kilojoules of work out of it. If, on the other hand, the delta G for a process is positive 100 kilojoules, that means that that process is not spontaneous. It doesn't happen on its own. So you have to put energy to get it to take place. And you have to put minimum 100 kilojoules of work to get it to take place. So it's a much more informative function than just delta S universe. So anyways, calculating delta G standard, again under standard condition, which means all partial pressures, reactants, products, if they're gases, is 1 atmosphere. Concentrations, reactant products, they're both present, it's 1 molar if they're aqueous, and if you have solids or liquids, they're pure. So for this reaction, we want to calculate delta G standard, which would be delta H standard minus delta T times delta S standard. So this is delta H standard. You use the heat of formations. You look up these values from the table, product minus reactant, the heat of formation of these. And then for S's also, you look the entropies, you look up those in the table too. So we calculated this earlier. This you learned from Chem 1A. I'm going to put a review video how to calculate this. So then you plug that in. The only thing is make sure you convert the joules into kilojoules, because usually delta S is in terms of joules, not kilojoules. So once you convert into kilojoules and these two have the same units, when you add them, you get plus 130 kilojoules. Now what does that mean? That means under standard state calcium carbonate, actually calcium carbonate does not get converted into calcium oxide and carbon dioxide. So when you have pure calcium carbonate, you have pure calcium oxide, and you have 1 atmosphere of carbon dioxide above that at 25 degrees Celsius, this reaction is non-spontaneous. To make it spontaneous, for every mole, you have to put in 130 kilojoules of work into it, 130 kilojoules of energy minimum into it to get it to work.